I want to go back to the space shuttle problem for a second. Let's talk about the space shuttle problem. The space shuttle problem is this. We have our space shuttle that is orbiting the Earth. Here it goes. And we want to raise it up to a higher altitude, okay, so that it can meet with, say, the International Space Station. If this altitude here, above the surface of the Earth, is h1, and we've got to get up to this altitude here, h2, how do we do that? We know how to do it in reality, right? You turn on your burners on the space shuttle, fires out the exhaust, goes up to this higher altitude. But how do we calculate how much work it's going to take to do that? Well, let's think about it from a slightly different point of view. Let's look at this system and consider conservation of energy. What can I say? When that space shuttle is in orbit here at altitude h1, it has some energy, E1. If I add some amount of work W to that initial energy, then I can get to the energy at this higher altitude. Right? This is just conservation of energy. Sitting there at E1, I add W, I'm going to get up to E2. Do we know what the energy is in a circular orbit? Do we know?
0.
No, it's not 0. It is, in fact, a negative number. How do we calculate the energy of a circular orbit? Well, we do the following. Energy is always kinetic plus potential. Kinetic is 1/2 mv squared. What's potential? Negative gmm over r. But we don't know what this speed is, v. Can we somehow relate that speed v to this thing over here? And the answer is yes, if I think about the forces in the radial direction. There's only one force in the radial direction which keeps this thing moving in a circle. It's Newton's universal law of gravitation. If things are moving in a circle, we know that the forces have to add up to mv squared over r. And now I can take this equation, solve it for 1/2 mv squared, and plug it in over here. Let's do that. I multiply both sides by r. I get a gmm over r equals mv squared. Then I multiply both sides by 1/2. So I get 1/2 on the left, gmm over r equals 1/2 mv squared. And now I put that into this equation over here. And look what we get. We get 1/2 gmm over r minus gmm over r. But that has common factor gmm over r. So it just becomes 1/2 minus 1, which is negative 1/2 gmm over r. So let's go back to this equation right here now and use this as RE. Negative 1/2 gmm over R1 plus W equals negative 1/2 gmm over R2. And now I can solve this equation for W. W equals, I'm going to add this to the other side, so I get a 1/2 gmm over R1 minus 1/2 gmm over R2. I have some common factors there, and so I can pull out a 1/2 out in front, a gmm, and then I have 1 over R1 minus 1 over R2. This is a positive number. Why? Because R1 is smaller than R2, which means that 1 over R1 is bigger than 1 over R2. Okay? You can plug in numbers here now if you know those values, and you have to remember that R1 is the radius of the Earth plus h1. R2 is the radius of the Earth plus h2. We would have to give you the mass of the space shuttle as well, but if you have all those numbers, you can plug them in. So, when we did this problem a second ago, is this the answer that we came up with? We just did the same problem a second ago, but we did it slightly differently. How did we do it? We integrated the force that distance. And when we integrated the force over that distance, did we get the same answer? Anybody write it down? It's different. Isaiah, what's different about it?
The half wasn't there?
The half, right? When we did the integral of f dr, we ended up, not with this, but gmm 1 over r1 minus 1 over r2, no half. So what did we do wrong? Did we do something wrong here? Or did we do something wrong there? The answer is we did something wrong here. Okay? Why is this one wrong? Because we were assuming that there's no change in the speed of the space shuttle going from here to here. But there is a change in the speed. We know that if you're up at this orbit, you don't have to be going as fast as when you're at the lower orbit. Okay? And so we did the wrong calculation integrating the force over that distance. The right way to approach this is from conservation of energy. Okay? Tricky. Valuable lesson. Something I didn't think of originally. Okay, any questions about this stuff? Does it make sense that this way would lead to too much work? Yes, because you don't have to be going as fast when you're up at that altitude, and that's where this half comes into it. You don't, in fact, need to do that much work. You need to do half that much work.